Hello, and welcome to session 3 of HEI's virtual workshop on health applications for satellite-derived air quality. Session 3 is on pushing the methodological limits on satellite use in health applications. My name's Allison Patton. I'm a senior scientist here at HEI, and on behalf of all of us here, I'm happy to welcome you to this workshop. Now, just a few things before we begin. All attendees are muted in view-only mode. There will be a Q&A period after the presentation, so please submit your questions via the Q&A function at any time during the webinar. You can also upvote questions in the Q&A. If you experience any logistical difficulties, please contact us using the chat box. All the slides and video from today's webinar will be available in the coming weeks. Please check the HEI website for details at the URL shown on the slide and also being posted into the Zoom chat. And we're also interested in hearing about your work on satellites, air quality, and health on the pre-workshop survey. Even if you haven't done work with satellites before, we're very interested in what you've learned, what you want to learn about satellites, and how you intend to use the data at some point. If you have any questions for the roundtable discussion, we'd be happy to see those in the survey as well. Now, just for anyone who's new to HEI, we're an independent nonprofit corporation chartered to provide policy relevant, high quality, and impartial science. Our funding is joint from the government and the worldwide motor vehicle industry, as well as some private foundations. All of the funding of research, it's conducted, and all the research is overseen and reviewed independently of HEI's sponsors. Additionally, the committee that selects and oversees research is completely separate from the committee that reviews and critiques research before it's published. We publish all of the results, both positive and negative, so there's a full record of the studies, and we do not take policy positions. If you are interested in learning more about HEI, there's a slightly longer version of this overview in session 1, or you can see our website for more details. From time to time, HEI will hold a workshop like this one to learn about the state of the art in a certain area of research. And this workshop is being held for the HEI Research Committee to learn about what research needs might exist for satellite-derived air quality, and particular in applications to health research. The chairs of this committee the chairs of this workshop from the committee are Dr. Heather Holmes and Dr. Jeff Brook, both who are on the research committee. And so this is session 3 of 4 in the workshop. The first 2 sessions were on setting the stage and on global applications of satellite-derived air quality data. And the final session to be held in a few weeks will be a roundtable discussion on what we learned and what that might mean going forward. Today, will be the agenda that we follow. The chairs of the session are Heather Holmes and Young Liu. We're starting with a few opening remarks, then each speaker will have about 20 minutes to present and 5 minutes for brief clarifying questions. And then we'll have open Q&A for questions from the chair and from the audience. So we hope to hear your questions for the speakers. These are the speakers for today's session. Dr. Dan Goldberg, Dr. Hisung Chung has prepared a presentation with Dr. Chun Kim, who can unfortunately not make it today because he's in Korea, and so the time zones don't exactly work for that. And finally, Dr. Sally Pusede will be presenting her work. So now I pass the mic to Dr. Heather Holmes to give some brief opening remarks and introduce the first speaker.
Thank you, Allison. I'm going to just give a quick introduction here because I don't want to take time away from our great speakers today. In session 1 of this webinar series, we provided a quick overview of the development of satellite-derived air pollution data and its applications. Using satellite remote sensing to study air pollution and environmental health was not part of the initial design of these satellite instruments. And we're really familiar with these instruments now, such as MODIS, MISR, OMI, VIIRS, and GOES. And over the past 2 decades, we've come a long way as a community to develop valuable air pollution data products from these instruments. And we've demonstrated their value in air quality management, air pollution exposure assessment, air pollution related disease burden estimation, and environmental epidemiology. Although there are still challenges, we can now refer to an increasing body of literature showcasing the many strengths of these satellite-derived data products. Resources and expertise are also available to help new users overcome the initial hurdles so they can start enjoying the unique advantages offered by satellite remote sensing technology. In the last webinar in session 2, it was demonstrated that satellite-derived air quality data has now not only allowed us to look at air pollution patterns and time trends in data-rich regions of the world or at the global scale, but also the satellite products have become a powerful tool to decolonize environmental health research. As we saw in that webinar, the air pollution health effects research in new regions of the world, such as India, Colombia, and South Africa, are now being led by researchers in those countries. So far, our discussions have mostly focused on the most mature satellite-derived air pollutant, which is PM 2.5. It is by no means the only parameter that can be estimated with satellite remote sensing data. And in today's presentations, we will see this expanded by introducing applications of satellite-derived trace gas species, such as NO2. And not just once a day from polar orbiting instruments, but also multiple times a day from a geostationary platform. We will also hear the speaker's thoughts on expanding the use of satellite-derived air quality data into new research areas such as environmental justice and health disparities. And now we will get started with our first speaker, Dr. Dan Goldberg, and he is an assistant research professor at George Washington University.
Thank you, Dr. Holmes. I will share my screen. I will assume you all can see it. Entering. There we go. Hopefully you all can see. If you cannot, please interrupt me. So good afternoon, good morning, good evening, wherever you are. Thank you for coming to this webinar series. It's an honor to be here and speak with you all. Today, I'll be discussing my work on quantifying and communicating uncertainty in air quality estimates. My name is Dan Goldberg, and I'm affiliated with George Washington University. Most of my presentation today will discuss information from the tropospheric monitoring instrument located here on the screen. This is installed on the Sentinel-5 precursor satellites. And next, you'll hear from Dr. Chong about the newest geostationary satellite for trace gases called GEMS. So I'd like to first show you some nice images from TROPOMI. I'm going to be talking about nitrogen dioxide for my presentation today, but much of what I am going to be discussing is generally applicable to other trace gases with some caveats and generally a little bit more uncertainty. Before going any further, I need to express my sincere appreciation for all of my collaborators. Only a small amount are listed here. I also want to express appreciation to NASA and a specific organization called HACAST. We're actually having an annual meeting in a few weeks. I encourage you to check out the website hacast.org. And I want to thank them. They've supported almost all of the work you're going to see today. So let's get right to it. How is satellite data useful? Let's address the elephant in the room at first. Is satellite data supposed to replace all ground monitoring measurements? And the answer is unequivocally no. Ground monitoring measurements will always be needed as reference data and can be used to help validate satellite data and can help with, especially when they overlap in time and space. Satellite data will also not replace bottom-up emissions inventory development, such as tracking fuel usage over time. But what satellite data can do is it can help develop near real-time regional trends in urban and rural areas. It can help us get a better sense of air pollution in areas in between monitors, such as locations with power plant emissions or unexpected emissions, such as wildfire emissions. Satellite data can also be used to help develop aggregate emission estimates from large sources and cities. And finally, just another example of how satellite data can be useful is to combine with models and land use information to estimate ground level concentrations for health studies. In particular, the last point I want to express some new advances, and I'll show this, is that satellite data has very high resolution these days, and it can be used to diagnose intra-urban gradients. So I think it's really important to understand that satellite data can be used for urban studies and in understanding the urban scale gradients. So as promised, this presentation will also focus on giving a general sense of the uncertainties surrounding satellite data. As we go across from left to right on this table here, we get an increase in uncertainty. Green represents less uncertainty, yellow and orange represent more uncertainty. For satellite data aggregated over a year or multiple years, there is generally less uncertainty than when using satellite data over a single day. And this is because random errors and random fluctuations in weather conditions tend to cancel out over time. As we move down the table, we can see an increase in uncertainty and complexity as we process the satellite data for different types of applications. If we're using satellite data to just get a rough spatial estimate of nitrogen dioxide, we should have pretty high confidence in this. Similarly, if we want to get NO2 trends over time, we should have pretty good confidence of this, especially if it's aggregated to the monthly timescale or longer. But once we start manipulating the data a little bit more, such as estimating surface concentrations from the column contents, the satellite data is giving us column information, or estimating emissions, or trying to infer CO2 emissions from the NOx emissions, there tends to be a little bit more uncertainty with those types of applications. I also want to show that there's generally a little bit less uncertainty for urban studies and a little bit more uncertainty for rural studies. And this is because in rural areas, the satellite instrument is near its detection limit. And also it's harder to disentangle anthropogenic, geogenic, and biogenic signals in rural areas. And finally, I want to just emphasize that this table is made specifically for nitrogen dioxide. If we wanted to do some studies, for example, using formaldehyde or carbon monoxide or methane, generally the uncertainties would be a little bit larger. So why is nitrogen dioxide itself an important pollutant? Typically, we think about nitrogen dioxide as a contributor to ozone and particulate matter formation, and this is definitely true. But NO2 is also a marker for traffic-related air pollutants such as diesel, PM, VOC air toxics, and when combined together are associated with respiratory effects such as asthma. Just a few months ago, our group published a paper showing that about 2 million children developed asthma due to nitrogen dioxide pollution globally. This is responsible for approximately 16% of all new pediatric asthma cases. NO2, as you'll hear later, is inequitably distributed across the urban landscape. Racialized, marginalized, and minoritized communities experience higher levels of this pollutant, and you'll hear about that in about 45 minutes. And also, nitrogen dioxide impairs natural visibility. This is the case in, say, natural parks, but also certainly in urban areas. So there was a reference to polar orbiting versus geostationary satellites, and let's discuss exactly what that means. The two instruments that I'm going to be showing, information from the two instruments I'm going to be showing are from the ozone monitoring instrument and the tropospheric monitoring instrument. Both of these are polar orbiters. OMI has a data record from about October 2004 to present, and a spatial resolution of approximately 24 by 13 kilometers squared. This data set is almost 18 years at this time frame. TROPOMI has 4 years worth of data, was launched in fall of 2017, and it has data since May of 2018, and has a spatial resolution of about 5 by 3 kilometers squared. These are polar orbiters, which means that they go from pole to pole, and with acquiring data in between the poles. And as alluded to before, we're gonna get an understanding of the GEM satellite, which is geostationary and has many more snapshots per day, 12 snapshots, up to 12 snapshots per day, but is only located over a single region of the globe. So what does NO2 satellite data look like on a day-to-day basis? I process these data in near real time for the United States and parts of Southern Canada. The website is here, tropomino2.us. I encourage you to check it out. But here's just an image from last Friday that I just quickly downloaded. We can see Los Angeles, the NO2 in Los Angeles. You can see some of the NO2 associated wildfires in New Mexico. We can also see Toronto and New York City in the eastern part of North America. And if we zoom in on this part, we can start to pick up on the fine scale plumes associated with the cities in these regions. In addition to New York City, we can see Philadelphia, the Baltimore-Washington corridor, and Pittsburgh. And if you really squint a little bit, you can see some of the power plant plumes in Western Pennsylvania and West Virginia. So this is quite amazing that TROPOMI can pick out individual power plant plumes on single day overpasses. And so once we average that data over 4 full years, I've updated this to be very recent. We can take a nice snapshot of the entire United States and Southern Canada and parts of Northern Mexico. We can see all the large pollution sources attributed to nitrogen dioxide or NOx emissions. We can see cities, we can see power plants, we can see industrial areas. We can also see some highway systems in the Western United States. I think this is quite amazing. But what's also nice about this is that you can compare any location in the United States to any other location in the United States, and additionally to any other location in the globe. So what I did is I found the area with the largest NO2 that happened to be East Los Angeles, and then compared that to, say, New York City, which has a value slightly lower, but not that much lower, between Brooklyn and Manhattan. And then right below that is the Port of Newark, New Jersey. So still some quite polluted locations in the United States. Now, zooming into some of these cities, we take a look at, say, Los Angeles and Chicago, shown on the far left. If we take a look at, say, the airports actually show up as secondary maxima on the outskirts of the major metropolitan areas. In the Chicago area, you can see the bottom left, we can see the US Steel Corporation industrial activities. And in Houston, we can see that the petrochemical complex in the Houston Ship Channel very clearly shows up. In each case, we're not discovering new sources of pollution. In fact, what's nice about this is that the areas that we think have large amounts of pollution, the satellite is actually confirming this. And it gives us a capability to quantify the pollution in ways that were not possible any other way. This should give you confidence that if the satellite is observing large amounts of nitrogen dioxide pollution elsewhere around the globe, that it's in fact a true enhancement in cities such as in Africa or the Middle East. I also want to compare the quote unquote new technology to older technology. In the left center, I'm showing the TROPOMI observations for 1 month, 1 week, and 1 day. And I'm comparing it to the exact same time frame of OMI, since they do overlap for several years now. It's very clear that TROPOMI has clearer pictures, especially at the weekly and daily timescales. However, this comes at the expense of having shorter data record of only 4 years, where OMI has a data record of almost 18 years. So if your application is concerned with something occurring within the last 4 years, I would generally recommend using Trope OMI data. If your application is concerned with long-term trends, I would recommend using OMI. So now transitioning a little bit to OMI and some of the long-term trends that have been seen from this instrument. I've taken a look between 2005 and 2019 at the trends in various parts of the world. In North America and Western Europe, we see pretty large decreases over this 14, 15-year time frame. In India, we see increases. And in China, we see an increase between 2005 and 2012, and then a decrease between 2012 and 2019. And elsewhere, it's a little bit more mixed, but certainly I would say in the Middle East and parts of Latin America, there have been more increases than decreases. If we just isolate some of the cities, I've done this for 80 cities globally, and I'm only showing 4 here for brevity. If we're going to compare the satellite, which is the black, to various different emissions inventories, which are the various colors, I want to note that the map city inventory is a somewhat outdated emissions inventory, so take that with a grain of salt. And for New York City, we can see that the satellite, which is black, compared to the colors, agrees very well. In Paris, we see the trends agree pretty well, but that the magnitude of the emissions appear to be underestimated in the emissions inventory. Similarly, in Santiago, Chile, we see also an underestimate in the inventory, but also a discrepancy in the interannual trends. And finally, in Dubai, we see relatively good magnitude, but definitely not a good estimate of the trends over time, where the inventory show an increase, but the satellite shows relatively flat over this 15-year period or so. If we now take a look at Los Angeles, here are the NOx emissions changes in Los Angeles on the top panel, but then on the bottom panel, I'm then inferring CO2 emissions from the NOx emissions using the NOx to CO2 ratio from the US EPA emissions inventory. And so the most encouraging part about this is that when there's an overlap with a major field campaign in the Los Angeles basin in the 2014-2015 timeframe, we get pretty good agreement between this method, which is inferring CO2, and the rigorous field campaign that occurred during this same timeframe. So I think this is a very preliminary way of looking at the data, but I think it's important to just show this methodology as a proof of concept. One other thing that we can do with satellite data is to estimate surface concentrations. But first, we have to see how well is the satellite data correlated with the surface measurements, and the answer is it's very, very good correlation, R squared of about 0.66 compared to the US EPA monitoring measurements. There are some grayed out points, and those are the locations that are qualified as near road. Typically, those are within tens of meters of a major highway. And so it's not fair to compare a satellite data set that has a spatial resolution of 3 to 5 kilometers to something that is a spatial gradient of on the order of tens of meters. So taking those out, we can see a very nice correlation. If we compare to the WHO guideline of 5.3, we can see that there's several locations in the United States that still exceed this guideline. What's also nice about this is that we can get a very, very rough estimate of the surface concentration simply by using the satellite data. We say 0.2 times 10 to the 15 molecules per centimeter squared, a very, very rough estimate of 5 ppb of NO2, and if 1 times 10 to the 16, you get somewhere around 18 ppb. Again, very rough estimate, but at least we're getting in the ballpark of range of what the actual surface concentrations are with very quickly. In a much more complicated way, we can use satellite data and land use parameters to estimate global surface NO2. And this has been a big endeavor by a colleague at Oregon State, Andy Larkin. We've been working on this project as supported by HEI. And we've done this everywhere. You can see some insets for various cities. Generally, the model performs better in the North America and Europe because there are more monitors to train the model. So it's important to note that these types of projects are still dependent somewhat on the ground monitoring networks. And there's the worst performance in Africa, Middle East, and Oceania, where there's not as many monitors. So just very quickly, some other applications of satellite data, which I did not have time to discuss today, but wanted to very briefly show you. For example, we could use satellite data to rapidly assess the changes during and after the COVID lockdowns. I've published a paper on this, and there's been many other colleagues that have done similar such work. We can investigate pollution, environmental justice communities, and Dr. Busede will talk about that in about a half hour. We can quantify emissions from oil and gas activities, including leakage rates. We can investigate biomass burning emissions. We can quantify biogenic or geogenic sources of trace gases, and sometimes these can have adverse health effects. And we can also use it as an indicator for economic activity. In 2009, we saw a very sharp decrease in NO2, and this corresponded to the economic recession in North America. And there's many more applications that I haven't even had time to list on this additional slide. So I'd want to leave you with this here is that there is an integrated air quality observing system that I think satellite data fits in quite well with. Satellite data can be used in isolation, but it can also be used in combination with other things such as model simulations. It can be used with high quality monitors. It can be used with intensive field campaigns such as ships and aircraft. And it can also be used in combination with low cost sensors. So I think it's important to note that the satellite data is, in my opinion, better when it's combined with some of these things, but it can also be used in isolation if that's the only thing you have access to. So, and all of these things, the models and the measurements help improve the algorithm for the satellite. So just some conclusions that I want to leave you with. How can we monitor air pollution from space? NO2 is observable. The measurements have high correlation with ground monitors and can be used to track near real-time emission rates. What are some of the general uncertainties associated with satellite data? There's less uncertainty for polluted areas over long time frames. There's a bit more uncertainty for single day snapshots and in areas which would qualify as cleaner. What are some case studies that I've shown? If we average over long time frames, especially months to years, we can give high resolution snapshots, and you can further process these into, say, surface concentrations. How can satellite data be used to estimate CO2? Well, NO2 is a good tracer for combustion in many anthropogenic CO2 emissions. So I think this has been a new direction in the community in the last couple of years. And what's the future? I think that satellites plus models plus high quality sensors and low cost sensors are all needed to get a better understanding of our air quality globally. So with that, I thank you very much. My email is here, and I encourage you to follow me on Twitter if you have like to follow along. Thanks.
Thank you, Dan, for the great presentation. There are several questions already queuing up in the Q&A box, which is great to see. Thank you all for asking questions. Most of those I think will be relevant to a lot of the presentations, so we'll save them for after everybody's done speaking. So with that, I would like to introduce our second speaker, Dr. Hae-Sung Chung, and he is currently a postdoc at the Center for Astrophysics, Harvard and Smithsonian.
Thank you, Dr. Holmes. Let me try to share my screen. Yeah. So good afternoon. This is Hee-Sung Chong from the Center for Astrophysics, Harvard and Smithsonian. If you cannot hear me or see my screen, please let me know. Before I start my presentation, I would like to thank AGI for organizing this outstanding webinar and inviting me here. And I also thank the audience for listening to my presentation. As you can see here in the title, I'm going to talk about the interpretation and improvement of air quality data from geostationary environment monitoring spectrometer, GEMS in short. This presentation was prepared by me and Professor Jun Kim at Yonsei University, Seoul, South Korea, who is the principal investigator of the GEMS mission. Also, other than the two of us, there are lots of contributors to the successful operation of the GEMS mission. So I would like to thank all of the contributors. And now let me start my presentation. This figure shows the satellite instrument observing aerosols and gases from the past to the present. The squares, circles, and triangles represent the sensors observing aerosols, trace gases, and greenhouse gases, respectively. As technology advances, the newer instruments generally tend to be located on the lower left side in this figure, having higher spatial resolution and higher temporal resolution. Different colors in this figure indicate different channels. And today I will focus on color purple, which represents ultraviolet and visible. The sensors whose names are in blue here correspond to low Earth orbit, LEO, ultraviolet visible instruments, typically having 1 or 2 revisits per day. Then GEMS was launched in 2020 as a part of the first geostationary air quality constellation. This constellation includes TEMPO and Sentinel-4, which will be launched in upcoming years. And these 3 geostationary sensors were designed to monitor air quality every daylight hour, which is unprecedented. Let's have a closer look at the geostationary air quality constellation. The yellow boxes in this map indicate the fields of regard of GEMS over Asia, TEMPO over America, and Sentinel-4 over Europe, respectively. And in the table on the right, the most critical feature is that they all have 1 hour revisit. They observe key pollutants in the atmosphere with the common elements in red, including total and tropospheric ozone columns, nitrogen dioxide, sulfur dioxide, formaldehyde, glycol, and aerosols. The ground pixel sizes of these 3 instruments are typically smaller than 10 kilometers. So what is the benefit of applying geostationary satellites for air quality studies? Here is an example for AOD, aerosol optical depth observations. We brought a published study using the GOSI instrument. GOSI was a geostationary ocean color imager that observed aerosols as well over Asia since 2011. These scatter plots here show that the GOSI AOD product on the right had several times larger number of data points compared to these low Earth orbit sensors for the same time period. The larger number of data samples is advantageous for applications. And in terms of daily spatial coverage, GOSI in black had significantly larger values than the 2 low Earth orbit sensors in red and blue. This advantage is coming from the higher observation frequency. So as Dr. Goldberg mentioned in his presentation, the random uncertainty and meteorological effects cancel out by averaging. So when we want to generate gapless satellite data for applications with kriging or any other methods, the frequent sampling facilitates reducing the time interval between data sets. This advantage matters because a map produced by just single satellite scan likely has spatial gaps due to some clouds. Despite these ongoing advances, there are still inherent challenges in the satellite data applications, regardless they are geostationary or low Earth orbit. First, satellites observe column amounts of pollutants typically, but most applications are interested in ground level concentrations. So therefore, an additional conversion could be required between these two quantities, depending on your application objectives. Second, cloud block the light passing through to the ground, increasing the errors in satellite retrievals. The most general way to treat cloudy pixels is to simply discard them by determining a specific cloud fraction criterion, which creates a gap in satellite data. Third, one satellite data point represents air quality of a certain area due to its ground pixel size. The larger the pixel size, the larger discrepancy from point measurements. Lastly, different species has different magnitude of uncertainty depending on their optical depth and absorption band. For example, SO2 here in yellow usually has relatively large percentage uncertainties than NO2 here in red in general, because SO2 has smaller optical depth and its absorption are interfered with by ozone. The uncertainties can be quantified by validation using independent observations, or can be estimated by the retrieval algorithms themselves. And in the latter case, estimated uncertainties are sometimes stored in the data files. So it is strongly recommended to have a look at user guide documents before applications. And this slide shows the GEMS east-west scan scenario. The GEMS field of regard here in orange curves covers from east of Japan to west of India. The scan schedule of GEMS was designed to move the field of view from east to west during a day to spend more time measuring ground pixels with low solar zenith angles. The low solar zenith angles generally lead to lower errors in satellite retrievals. So in the morning Korean time, we observed the yellow box and then the green box around noon. And lastly, the magenta box here in the afternoon. Currently, 4 types of field of views are being used, including half east, half Korea, full central, and full west. Considering that GEMS performs its scans 8 times a day on average, we can say that it has been generating over 10 million spectra every day. These are examples of the GEMS level 2 products retrieved from different states. Each and every product demonstrates its capability of capturing the diurnal variations of important air quality factors in East Asia. Here we see the transboundary transport of aerosols and distribution of total and tropospheric ozone and variations in surface UV. We also see changes in NO2 pollution, volcanic SO2 plumes, and organic compound concentrations within a day in Asia. And cloud and surface reflectance information is given as well. These are the results of GEMS level 2 product validation for August to October 2020. For the reference observations, we used ground data such as AeroNet and other satellite observations, including OMI, TROPOMI, and MODIS. The correlation coefficient written in red at each panel represents the good agreement between GEMS and the reference observations. However, we still see some discrepancies between GEMS and the reference data sets. So we will keep improving the data algorithm performance and the data quality of GEMS products for example, by updating air mass factors and calibrating level 1 data. This slide tabulates the GEMS validation results. The blue numbers represent the goal correlations, which were set before the GEMS launch. And the red indicates the achieved correlations. For the same period from August to October 2020, every product achieved a higher correlation than the goal. But again, validation is very crucial to estimate uncertainties and further improve the retrieval algorithms. So we have continued this validation on a monthly basis, and we'll do it in the future as well. Now I'd like to present some detailed examples of GEMS retrievals for each species. This slide shows the total ozone columns observed on October 19 last year. You can see that the GEMS results on the left are given by an animation, while Tropomi is given by a still image. The GEMS observations demonstrate diurnal variations of ozone over Asia with consistent spatial distributions with Tropomi. This slide shows a dust event on March 28 last year. The GEMS AOD product captures the dust plume very well, and it shows consistent features with the AHI AOD product. AHI is a Japanese geostationary sensor. One of the major instrumental differences between GEMS and AHI is their channel specification. For example, AHI has a wider slit width than GEMS, and it has IR channels, which are advantageous for aerosol retrieval and cloud screening. Meanwhile, GEMS has UV channels, so it makes GEMS has a capability of capturing aerosol signals over bright surfaces. The yellow box here highlights the advantage of GEMS aerosol product. The GEMS product has a higher spatial coverage here over the bright surfaces. And in addition to the AOD values, the GEMS aerosol algorithm produces single scattering albedo, SSA, which represents the absorption characteristics of aerosols and aerosol layer height. Then we looked into the GEMS aerosol retrievals for big Siberian wildfire in August last year. Very high AODs were captured in Mongolia from both GEMS and AHI. GEMS AODs show temporal and spatial continuity without being significantly affected by bright surfaces or clouds. Although it is not shown in this slide, the aerosol types detected by the GEMS algorithm here were highly absorbing fine aerosols, which makes sense for the aerosol plumes from wildfires. Now moving on to NO2 examples. As described in the last presentation and as will be described in the next presentation, NO2 is a very important species for interpreting and assessing the anthropogenic activities. So this animation demonstrates that now it is possible to assess the diurnal variations in urban scale NO2 pollution over Asia from space. This slide shows average diurnal variations of total NO2 columns from April to June last year at major cities in East Asia. In China, we focus on Shanghai, Beijing, and Tianjin. Among these three cities, Tianjin had the largest NO2 columns with diurnal variability of high in the morning to noon and low in the afternoon. And in Seoul, the total NO2 columns increased in the morning and decreased in the afternoon. We didn't have as many samples in Tokyo as in the other cities because of the scan schedule, but we observed flat temporal patterns in the morning. We note that the GEMS NO2 are considerably larger than Tropomi, so we have been investigating this matter, focusing on the differences in AMF between the two satellites. Using the GEMS NO2 retrievals, we could detect ship tracks in Asia. This slide shows examples in Southeast Asia. Some noticeable shipwrecks were found around Malaysia and Singapore with typically larger NO2 columns in the morning. Now I'd like to present SO2 observations. This is an example of volcanic eruption in August 2020 at Nishinoshima Island in Japan. The GEMS SO2 on the left and the UV aerosol index in the middle present clear signals around the volcano. Both GEMS products successfully demonstrate the flow of volcanic plume within a day, and the spatial distribution of GEMS VCD is consistent with that of tropomi. This slide shows average diurnal patterns of NO2 on the left and SO2 on the right from April to June last year. We noted the volcanic signals from the SO2 maps and marked them with these blue arrows. Meanwhile, we also found some large SO2 columns at megacities in Asia. The red squares on the maps indicate Guangzhou, Quanzhou, and Shanghai, which had both large NO2 and SO2 columns. So we will perform further investigation on these simultaneous emissions of NO2 and SO2, probably implying the extent coal burning from industries. This is an example of GEMS formaldehyde retrievals over East Asia in July 2020. The GEMS formaldehyde retrieval demonstrate large vertical columns over East Asia. We found an increasing pattern from morning to afternoon for this day in East China. So we will be able to verify these diurnal variations in Asia using ground-based observations such as Pandora and MaxDOAS in the future. The GEMS UV index product represents the variability of surface UV over Asia. It shows high values over low solar zenith angles and high terrain elevations, for example, over here, the Tibetan Plateau. This map indicates the ground-based instruments in Asia, which can be used for GEMS validation. We will pursue the validation for a longer and continued period, employing these instruments within the GEMS field of regard. At this moment, you can find and download the GEMS Level 2 images from the NIR website presented here. The data files, however, have not been distributed yet. So if you click the keyword dropdown on the webpage, the list of L2 pops up. Then you can find near real-time GEMS images for the products you are interested in. Now let me sum up my presentation. Despite these ongoing advances in satellite technology, several considerations are required for satellite air quality applications, including clouds, spatial resolution, and sensitivity. As a part of the geostationary air quality constellation, GEMS has been successfully operating since its launch in February 2020, capturing diurnal variations of aerosols and trace gases. Continuous validation of GEMS observations is very essential to improve the data quality. Lastly, these are examples of aerosol flow rate on the left and PM2.5 concentration data on the right from GEMS. They both are estimated using the GEMS AOD product with some other auxiliary data. As clouds, here in blank, move along the wind direction, the locations of available data points move as well. So it means some gaps can be filled after aggregating the data from different time, even for one day. So in this context, we expect that the high spatial temporal coverages of GEMS will provide some advantages in applications. This is all I have today. Thank you for your attention.
Great. Thank you, Hee-sung, for the wonderful presentation. Now we are going to move on to our third and final speaker. Dr. Sally Pasede is an assistant professor at the University of Virginia.
Hi, everyone. Thank you for giving me the opportunity to speak with you today. I'm going to go ahead and share my screen here. All right. So the title of my presentation is Observing NO2 Air Pollution Inequalities in US Cities from Space. This work is really collaborative, and I want to acknowledge my many co-authors here. And in particular, I want to acknowledge the work of two students in my lab, Angelique Dematillo and Isabella Dressel, who've done the vast majority of the work that I'm going to share with you today. So a little bit of background here. In US cities, it's widely established that air pollution is worse in neighborhoods where residents are primarily people of color and have lower household incomes. And to provide you with two definitions here to get us started, I want to start with the definition of environmental racism by Dr. Robert Bullard. Any policy, practice, or directive that differentially affects or disadvantages individuals, groups, or communities based on race or color, whether intended or unintended. The second definition comes from the US EPA, and that is of environmental injustice, which is any inequality and or inequity with respect to the development, implementation, and enforcement of environmental laws and policies. So inequalities, air pollution inequalities within cities cause measurable differences in health and life expectancy. And despite improving air quality in cities across the US, these air pollution disparities have been shown to persist. So I want to give you a sense for one of the challenges that faces research in this area, and that's an analytical challenge. And traditional routine monitoring has historically been unable to resolve neighborhood scale spatiotemporal variability within cities. So on the left here, I'm showing you an image from NASA's OMI. This is collecting data starting in 2004. And we can see here, this is a picture over Los Angeles, California. We can see that air pollution is high over the city of Los Angeles, but we have little information about how it varies within the city. This is important because when we're talking about a pollutant or any primary pollutant, in this case, I'm going to focus on NO2, the distance decay gradients away from sources are going to be around a few hundred meters to at most 2 kilometers. Okay, so we really need to have the opportunity to see these steep spatial gradients. I'm showing you here on the right, this is the US EPA monitoring network across the city of Los Angeles. And this is one of the best monitored cities in the world. There are more monitors in Los Angeles than any other city in the United States, but still fewer than 5% of census tracts in the city of Los Angeles live within 2 kilometers of a monitor. So we have vast regions of the city that don't really have their air monitored for NO2 pollution. So advances in satellite remote sensing bring new opportunities to observe neighborhood scale air pollution inequities, or excuse me, inequalities in cities. And in order to be able to do that, what I'll show initially in this research is 2 key requirements. And so these 2 observational requirements for environmental justice decision-making are, 1, that these measurements must resolve neighborhood scale NO2 differences. And when we're talking about differences between neighborhoods, we think we need to capture those dispersion decay gradients of a few hundred meters to a couple of kilometers. And the second is that spatial patterns in the column must reflect pollutant patterns at the surface. So in my work, we're not creating surface mixing ratio products, but we at least need to know that the patterns we see in the columns match the patterns that exist at the surface. The observational strengths with satellites, and I'm going to focus here on Trobomi, this is certainly going to be true with Tempo as well, is that these measurements are spatially comprehensive and they're collected daily, and they capture spatiotemporal patterns that are very useful for source identification. And I'll give you an example of this as we go forward. And one note I'll make is that it's generally been assumed in this research that some oversampling or time averaging is required. I'll come back to this assumption later on, but we'll go ahead and get started started here. So I'm going to show you some evidence that these tropomi data, at least in the case of NO2, meet criteria 1 and 2. Okay, and the way that we've gone about this in our research is, in order to know whether we can resolve inter-neighborhood differences, is we need some kind of high resolution calibration standard. Effectively, we need a standard against which to compare. So we've taken advantage of high spatial resolution airborne remote sensing. This is an image of observations collected over the city of Houston during the 2013 Discovery Q mission by the GCAS instrument. And GCAS makes hyperspectral measurements of backscattered solar radiation in the UV. It has a 2D CCD array detector for 2D NO2 mapping, with the long track coverage taken care of by movement of the host aircraft. The native spatial resolution is on the order of tens of meters, but some spatial averaging is required for signal to noise. And the retrievals used in these data are similar to those of major satellites like tropomi. Okay, so it makes the comparison relatively straightforward. But here you're looking at the city of Houston, Texas, and we can see very elevated NO2 over this polluted region called the Houston Ship Channel. We can also make out in some cases these points like the Texas City refinery and some major roadways and some things like that. And so having a spatial resolution here of 500 meters by 250 meters, now we're actually going to have the ability to subsample neighborhoods. And in this case, we've defined them as census tracts. So we can use these high spatial resolution airborne observations to compare the tropomi data. And on the left here, you're looking at a map of tropomi. This is averaged over a year, okay? And then we take those data and we average them to the neighborhood scale defined as the census tract. And this allows a comparison with the neighborhood demographics and economics. And we can test that for the full Houston metropolitan area or just along the flight path of the high spatial resolution observations. And what we found in the city of Houston is that the high resolution airborne observations match the tropomi data averaged over the course of a year or a month to within associated uncertainties. Okay. We can look at this comparison another way. And in this case, we're looking at the tropomi observations throughout the city of Houston in income and race ethnicity space. So household income is on the y-axis here, and the census tract fraction of non-white and/or Hispanic residents is located here. Okay, the coloration is that the red data represent the highest NO2 quintile, the yellow are the intermediate NO2 quintile, and the blue are the low NO2 quintile observations. And we can see that the highest NO2 levels are concentrated in census tracts with the lowest household incomes and the largest proportion of residents who are people of color. And we're going to continue that comparison with the airborne observations. Here we're looking just along the airborne flight track as well. And then over on the right, we can see the airborne flight composite. And in conclusion, what we see is that also in this race, ethnicity, and income space, the high resolution airborne observations in tropomi capture similar NO2 patterns as each other. We do start to see differences here. You'll notice in the color bar, these observations are normally distributed. In the case of in the GCAS flight observations, they're log normally distributed. So we're missing a lot of those very high values in part because of issues in retrieval and also due to the time averaging. But yeah, we see that these airborne observations and the satellite data are giving the same answer to within the associated uncertainties. So now getting to this question about whether the spatial patterns in the columns reflect those at the surface. And we've looked at this issue in two ways. Again, we're looking at the city of Houston, and each one of these circles represent a surface NO2 monitor, and the coloration is telling us what that mixing ratio is in that location. And we're going to do a correlation analysis with the columns above, but we're going to do it as a function of distance. So here on the right, you're looking at the correlation coefficient between the satellite column and the surface monitor. And we're going to do that as further and further distances away from the monitors. So we can see the correlation coefficient between the observations are very high for the directly overhead columns, but very rapidly they start to fall off. Okay, and this actually tells us something about the system because the fall off in these correlation coefficients is reflecting those distance decay gradients in NO2 that we expect. The second way that we've looked at this relationship between columns and surface distributions is actually in Houston, we actually have the opportunity to look at a very large number of NO2 vertical profiles. In this case, over 144 in situ NO2 vertical profiles throughout the day. Okay, so we statistically analyze these vertical profiles throughout the city, throughout the day. We find, as we expect, the vast majority of NO2 pollution is in the layer of the atmosphere nearest to the surface. We don't find differences, at least on the scale of Houston, in those heights. And we can also kind of vertically parse that pollution, comparing things like the full column, or sorry, the column integral within the boundary layer to the full column integral. And we don't, again, find much location dependent differences between the throughout the city, excuse me. Okay, so here we're starting to feel confident that the spatial patterns in the columns are matching those spatial patterns at the surface. So from there, from our detailed investigation of how and when these satellite observations apply in the city of Houston, we scaled this up to 52 major cities across the United States. In this case, we're defining them as census designated urbanized areas. This is really the urban core of a city. So we're not looking at urban suburban gradients. We're looking within the cities themselves. We take 2 years of tropomi observations. We oversample them to 1 kilometer by 1 kilometer, and we average them to the census tract. We population weight the columns by race, ethnicity, and sort them by income and poverty status. And we compute the inequalities over the full time record seasonally and separately by weekday and weekend. And this is where we're really going to start to take advantage of the temporal variability that's connected to variability in emissions. So to give you a sense for our results here, we see average inequalities in these 52 cities for Black and African Americans of 17%, Hispanics and Latinos of 19%, for Asians of 12%, for Native Americans of 15%, and for people living below the poverty line of 15% as well. And when we combine race ethnicity, we see that people of color in low income tracts have on average inequalities on the order of 28%. But you can see the data for that metric here on the right, and there's pretty substantial variability across the city. And in some cities, particularly large and polluted cities, we see inequalities that are much higher. This is around 40%. We have Los Angeles, Phoenix, New York, New Jersey, Chicago, for example. So in some places, these inequalities are double the national average. So we still want to learn about what these tropomi observations can and can't do, but we don't have airborne observations in all 52 cities. So we need to think of new constraints on what the satellite can and can't resolve. So in this case, we're taking advantage of relationships in the spatial structure of residential segregation. Okay, and I'm just going to show you that in all US cities are segregated, but the spatial structure of that segregation is different. And they're going to range on this spectrum between segregation that's clustered. So you can see if each one of these circles is a census tract with some race, ethnicity, population, that they're going to have sort of that the demographics within one census tract are similar to those to the census tracts around it. So we have spatial aggregation of demographics. Or in the case of patchwork, every census tract is segregated but different. And so if the resolution of tropomi challenges the ability to resolve these inequalities, we should better be able to discern inequality in cities characterized by clustering and patchwork. And what we find in this work is that there's no relationship between inequality and segregation structure. So we conclude here that tropomi is in fact resolving these tract scale inequalities, even when segregated tracts do not aggregate into larger spatial regions. Also in this work, we've repeated our sort of distance dependent correlation analysis and got similar results as in Houston. Okay, so one of the main advantages of having satellite observations is the temporal variability that's built into the data set. And in the United States, we have this well-known experiment called the weekday experiment, where we see large differences in emissions on weekdays compared to weekends. So diesel engines are a major source of NO2 in US cities. They also emit a wide variety of other toxic air pollutants, okay? And they're known to be environmental justice issues. This is an image, this is weekdays across the United States, and this is weekends. So we have this really large perturbation to the sources where a very large portion of diesel trucks are parked on weekends. So we're going to use this weekday experiment to identify the portion of inequality that's caused by diesel trucking. Okay. The other thing that's important to note here is that there aren't large changes in other sources as well. So while the timing of gasoline-powered vehicle traffic may change, the actual magnitude is relatively constant. Okay, so in order to do this, we need two things. We need to figure out what portion of diesel vehicles and other sources are parked on the weekends. Okay, so we need to know the actual change in emissions. And to do that, we use two inventories. We combine an inventory called the fuel-based inventory for vehicle emissions. This is a high spatial resolution inventory by 4 kilometers by 4 kilometers. It's hourly and monthly and daily resolved, okay? And it gives us the on-road and off-road gasoline and diesel emissions. And we compare that with the national emissions inventory. And from this, we can see that diesel emissions are reduced by on average 60% weekday to weekend across the United States. So one of the things we investigate at this point is, well, 4 kilometers by 4 kilometers, that's a lot coarser resolution than 1 kilometer by 1 kilometer. So we have to kind of first say, well, is the change that we see due to these weekday weekend patterns and emissions, are we really just seeing a change in the power of our observations because we've degraded the spatial resolution? So we do this sensitivity study here where we degrade the tropomi observations to 4 kilometers by 4 kilometers. And in fact, what we find is they capture equivalent inequalities as the 1 kilometer by 1 kilometer. And I think this is a little bit surprising, but we'll come back to that. In fact, we actually see that the inequalities are slightly higher in most cities, okay? There's a few exceptions here. We do see large negative biases due to this sort of degradation of the resolution in places like San Francisco and Oakland. And these are very narrow cities up against the ocean. So in fact, maybe even they're challenged by the 1 kilometer by 1 kilometer observations. So the change in emissions themselves doesn't tell us the change in pollution because we have to account for atmospheric and chemical lifetime effects. And this is where the observations really come in handy. So on the x-axis here, you're looking at NO2 neighborhood level inequalities on weekdays. And we correlate that against neighborhood level NO2 inequalities on weekends. And we use this correlation to derive the response to the change in emissions weekday to weekend. And we find that NO2 inequalities themselves are reduced by 37%. The data here are actually separated by season. The gray data are in the summer and the blue data are in the winter. So you can see that when the NO2 chemical lifetime is short, the correlation is much tighter. But from this, we can derive this policy relevant conclusion that a 60% reduction in diesel NOx emissions causes NO2 disparities to decrease by 40%. And somewhat sort of serendipitously, this is actually the exact sort of predicted change that we should expect from this new Biden administration rule on heavy duty diesel trucking, where they're predicting that by 2045, we're going to see a reduction in NOx emissions from diesel truck by 60%. So in effect, we've kind of tested the outcome of that new policy. So in my last few minutes here, I want to show you some new work. This isn't published. But you know, from our work across the United States and thinking about what happens when we degrade the tropomi observations to coarser resolution and seeing we can still see those NO2 inequalities, it seems that maybe we don't actually need such high spatial resolution observations. So in this case, we're going to test that, and we're going to do so because perhaps we get more information when we can enhance the temporal information, right? So past approaches have relied on oversampling to improve observational spatial resolution. And the effect of this has been to trade away a lot of the temporal information. So in order to do this analysis, we're going to go back to the aircraft observations. In this case, this is the New York City, Newark, New Jersey urbanized area. And there was a NASA-led mission there called LISTOS, where they again collected these high spatial resolution airborne remote sensing observations. These are resolved to 250 by 250 meters. So again, we're really subsampling the vast majority of census tracts throughout the region. In the center here, you're looking at a single tropomi scene. And then on the right here, you're looking at oversampled tropomi data for over a single year. And these data have all been averaged to the census tract, which is why their borders are a little bit fuzzy. So we can use these airborne observations and tropomi observations. And the good thing was that LISTOS took place in 2018. So we can actually directly compare coincident points. Okay, so you're looking here for one inequality metric. The airborne inequality is on the x-axis, here as a percentage, and down here as an absolute value. And the tropomi inequality is on the y, here as a percentage, and here as an absolute value. And we've built a correlation and slope for each of our inequality metrics. And what we find is that the data are very well correlated, and also that the slopes are pretty high. So at least in the case of the New York City, Newark, New Jersey urbanized area, these daily tropomi observations, even though they have coarser spatial resolutions, are actually capturing as much as 75% of local inequality within those cities. In some cases, it's much, much higher. You can see this column of slopes here and these very high correlation coefficients. Okay. So now we take these daily tropomi observations, and this gives us an opportunity to really explore some of the issues in these observations. So the first thing that we do is look at the results of inequality as a function of coverage. And so this is UA coverage, but this is the urbanized area coverage. So this is how much data we have that covers New York City and Newark, okay? And so when those coverage levels are low, these are the mean inequalities in terms of percent. You can see that these inequalities are low. Oops. These inequalities are low. But when we increase the coverage levels to 30 to 60% or greater than 60%, these numbers get higher. And the cause of this is that when we have low sampling coverage, what happens is we're not sampling neighborhoods with populations of key demographic groups. So it's interfering with the inequality analysis, okay? And this coverage, this is going to be caused largely by the presence of clouds, okay? So these would be clearer sky days and these would be very cloudy days. We also can look at the impact on the daily observations themselves. This is the coefficient of variance in the daily observations for our various inequality metrics. And you can see here that for very low coverage days, this coefficient of variance is much higher. It improves with higher coverage and improves even further when we have at least 60% coverage across the city. Okay, so not only are the means sensitive to coverage, but also the daily results as well. All right, and so one test that we can do is we can certainly compare our mean daily inequalities to those values we get from the oversample data. And so these are the same mean inequalities that we just went through, okay? And these are the various coverage levels. And in this case, we're looking at the inequalities, and you can see here that these numbers, as long as we're hitting a coverage threshold of about 30%, the mean daily inequalities are agreeing to with the oversampling inequalities, okay? So pretty exciting in terms of what we can do with the daily inequality estimates. I did want to say one other thing. So we are sampling and we're sort of biasing our results towards clear sky conditions. One of the effects of that is going to be to bias our inequality estimates low. And the reason why we think that is because if you take the mean surface NO2 data on clear sky days across the domain, you get a value of about 8 ppb. If you look just on low coverage days or cloudy days, that value goes up to almost 13 parts per billion. And as I'll show you later on, inequality is very strongly correlated with overall pollution level. So likely what we have here is a low bias due to the fact that we aren't seeing conditions when clouds are in the sky. Finally, what I want to show you here, and I hope I'm doing okay on time, is that we have the opportunity when we look at all of these observations. We're looking at observations from May 2018 to September 2021. This is 4 years of data, and we have a wide variety of of spatial resolutions effectively. Okay, so this is the mean pixel area over New York City and Newark, and the mean pixel areas range between 20 and 90 kilometers squared. Okay, so a very large range in the spatial resolution, and this is the number of daily observations. And so keep in mind that these typical NO2 distance decay gradients should be on the order of a few hundred meters to 1 to 2 kilometers. So this is much coarser than we would expect we need. And we can use this as essentially an experiment to test how sensitive our results are to pixel area. And we find that in truth that the inequality estimates are largely insensitive to this variation across pixel variability until the pixels get to be about 60 kilometers squared. Okay, so the last thing I want to share with you here is what this gives us. Okay, so we've taken a lot of care to think through these daily observations, but what's the point of that? And so now we can take these daily observations and use them to build empirical relationships with other atmospheric variables that allow us to situate inequalities in the context of our understanding of air quality and climate change. Okay, and so here I'm showing you some of the information we get related to air quality in New York and New Jersey. On the right here, you're looking at NO2 inequalities, daily NO2 inequalities plotted versus surface NO2 mixing ratios. And these are strongly correlated. These are Spearman rank correlation coefficients. You see that it's about 0.75. And this is the absolute inequality, okay? So the more pollution we have, the more of it is ending up in communities of color and low-income communities. But when we look at the relative inequalities, we see this relationship break down, okay? In this case, we see an insignificant correlation between the relative differences in the surface levels. And what this is really identifying for us is this is providing direct observational evidence for the disproportionate siting of NOx emitters in these communities, right? We have really overburdened communities where if we bring down NO2 pollution at any of these sources, the relative disparities are persisting. The other thing that we can find, we can build this correlation against things like surface ozone. We find NO2 inequalities correlate significantly and moderately with ozone air pollution. And what this does is it tells us is if these NOx emission regulations target overburdened communities specifically, not only do we bring down burdens in those places, we actually would have regional ozone co-benefits. In terms of climate, we can look against things like changes in surface winds or temperature. And you can see here, this is the correlation between NO2 inequalities and surface winds. More frequent stagnation is predicted in New York City and New Jersey with climate change. And so we would imagine from these results that would exacerbate inequalities in the future. The other thing we can do is build correlations with summer temperatures. We find a weak but significant relationship between inequalities with temperature. So that would suggest that maybe there's not a strong sort of co-variation there, but what we would certainly expect then are greater cumulative burdens for overburdened communities for both NO2 and urban heat. So we really just kind of scratch the surface about what we can do when we can situate these inequalities in these air pollution and climate change contexts. So this is kind of my summary statement here that next generation satellite observations, both TROPOMI and TEMPO, they have the potential to deepen our understanding of air pollution inequalities in US cities, inform decision-making related to air pollution health disparities, and really support the demands people place on their policymakers. And so I'm just going to show one last slide and then I'm done. But really one further issue with these observations is even though they are available, they are certainly not accessible. So this is a tool that we're building to sort of an online tool that will allow sort of direct observation of inequalities within cities. This is Houston, Texas, looking at relationships between pollution, income, race, ethnicity, and sort of allow the opportunity for people to download data sets merged onto the census tract scale. So yeah, with that, thank you very much for your time.
Thank you very much, Sally, Isong, and Dan, for your presentations. Sorry that I'm a little late. Let's move on to the Q&A sessions. To our audience, please post your questions in the Q&A box. For now, I got a few technical questions. First one is for Hisong. Can you let us know how to access the GEMS data?
Oh yeah, can you hear my voice?
Yes.
Oh yeah, GEMS data sets have not been distributed to the public yet, but as far as I know, NIER in South Korea, who are in charge of operating GEMS, have planned to release some of the products within this year. So I think they will announce it through their website when they are going to release them. Okay, thanks a lot. And the next question is directed to both Sally and Dan. So can you provide a little bit of details on how you downscale TropoMe data to a kilometer or sub-kilometer scale? Who likes to go first?
I guess I can go first. I have developed code to do this in this software program that I use called IDL. I know this is not widely used by most people, but essentially what I do is I regrid the data to a fine spatial resolution. So natively, the pixels are about 3 by 5 kilometers squared, and then I regrid that to either 1 kilometer or 0.01 degrees, or sometimes even finer spatial resolution using software that I've developed myself. But I'm hoping to make this publicly available. There's some modifications that I need to do to make this used by all, especially, but also you'll need a license to use IDL. I think Sally is using a publicly available data processing, so I'd recommend probably her method.
So we use an algorithm produced by Kang Sun at the University of Buffalo. It's a physics-based oversampling algorithm. It essentially is a time average that takes into account the sensitivity distributions of the sensor when it does the averaging. And he has made that code publicly available, and he is also an excellent colleague to have as part of your team. He's a wonderful colleague, so I would encourage you to reach out to him. So we can only, with the oversampling, I will just say, you can go, in our case, we go down to 1 kilometer by 1 kilometer. In the case of the 50-meter product, that was a land use regression product, so that was a different thing. In the oversampling, we go down to 1 kilometer by 1 kilometer. And then that data is technically spatially continuous, and we take that and we average that to the census tracts using, we actually, rather than using GIS, we do that in MATLAB. But I don't know if Dan, you want to talk about the land use regression, because that's where it's going down to 50 meters.
Yeah, well, that's a whole different story. That would be some type of spatial interpolation, but yeah, that's a yeah, we won't get into that right now.
Thanks, Dan, Sally. Now a couple of open-ended questions. So in the first session, we talked a little bit about integrating sources of data through or across different technology platforms, and when you get this satellite-based data resolution down to kilometer scale, the goal is to characterize the finer scale spatial contrasts. What do you think of the low-cost sensors measurement in this space? I guess now it's mostly PM sensors are more available than trace gas sensors. But overall, thoughts on integrating satellite data with sensor data?
I could jump in here. I think for our work, that's been essential. I mean, we've sort of always started with what's the full suite of observations that we have available, and then how does that help inform our interpretation of the satellite observations. So we've been really eager to bring in as much information as possible, especially when we're still kind of trying to understand, to what extent is the satellite really actually resolving a census tract level difference. I think there's a lot of, there's still work to be done to answer that question.
I think, I think low-cost sensors can be used, even if they're PM 2.5 in comparison to NO2, as long as you do it appropriately. I mean, there's some sources that do have co-emissions of both at the same time. I think diesel trucks would be the best example, but something like wildfires would be another example where you get primary co-emissions of both. So I think you'd have to use them in a specific way, but I wouldn't at all discount using a PM 2.5 sensor for at least giving us some type of information about NO2, even though it is measuring as something completely different, because there are co-emissions between the two.
Great, thanks. Another question came up. This one is interesting. And the idea is, if you want to study air pollution disparities or, contrasts, wouldn't you consider a mixture approach, multi-pollutant exposure? And talking about NO2 and ozone, we all know the titration effect, and often in downtown areas you have this kind of a negative correlation between NO2 and ozone abundance. How do we consider inequality in that setting?
Yeah, so I think that's a really good question. I think that there's a few parts to the answer. One, we don't have all the data that we would want, right? In an ideal sense, we would want high spatial resolution observations of a wide variety of pollutants, not just to think about sort of pollutant mixtures and how they affect our health, but also because those pollutant mixtures are going to vary in ways that tell us about sources. I don't think we have to kind of make do with the observations that we have. I think that's one key thing. I do think that there's a lot of good work to be done. And one thing we're interested in is to what extent is the satellite column for NO2 telling you about other pollutants? Other pollutants are more difficult, right? You don't have the spatial resolution. Maybe those pollutants are longer lived. So they might be, they might be distributed differently vertically, right? In the case of NO2, by and large, it's very close to the surface. In the case of AOD, that might not be the case. It would be excellent to have ways to link the data that we do have to the data that we don't have. I think what you bring up in terms of ozone is a really good point. That's kind of where we're interested in sort of thinking about how we bring information on or sort of research on inequalities into our broader understanding about air quality, because they're largely separated. In our case, what we did was we take inequalities across the city and we correlate them actually with the highest ozone value anywhere in the domain. And so we tend not to see large inequalities in secondary pollutants like ozone. There is work out there to show that. There's some recently published work by Jillian Marshall that shows that. But I do think in more and more cities, there's other research to suggest that we're moving towards NOx limitation, even in really major cities. So it would start to make sense that we start to see more of a positive and proportional relationship between NO2 and ozone. I think what it does say is in these places where there's a lot of sources, because it's not evenly distributed across the city, if we control NO2 in those places where there's like real hotspots for pollutant, it does seem from our work, there's still, I fully agree there's a lot to be done, but it does seem from our work, at least in New York City, that will have a good effect on ozone. But there's lots of work to be done.
Well, that makes this field exciting, doesn't it? Dan, any comments on that? Mixture?
Yeah, I mean, I really echo a lot of what Sally just said, but which is an excellent response. I guess I would just also say that one of the main reasons I focus on nitrogen dioxide is because of its spectroscopic features and because it is, I think, the best trace gas that can be observed by satellite data sets, by satellite instruments. So I would love to focus on, say, an ozone satellite measurement, but it's just much more difficult to retrieve, near surface ozone from satellite instruments. So it's not that we're, actively trying to, focus on an NO2 just because we like NO2. It's because of the spectroscopic features, and it is the easiest to do these types of studies. And we know that there are disparities with PM 2.5 as well. So, yeah.
And maybe one way to kind of to sort of add information there is that, one thing about NO2 that's great is because it is so short-lived and it's emitted by a whole wide variety of different combustion sources. If we can take advantage of the temporal variability we see from space and NO2, and we can sort of say, well, this is from diesel trucking, or this is from power plants or airports, maybe we can add information in there because we do know something about the other types of pollutants that are emitted by those kinds of sources.
That's a very interesting potential solution when you kind of bring in the spatio-temporal aspects of different pollutants, right? Something like you're trading the spatial, or you're trying to introduce information from the frequency space together with the Euclidean distance space. That's great. So while we're waiting for other questions to come in, I have a question for Hisong. When I first introduced Tempo, we said, well, that's part of a international coalition or a constellation of geo missions. And I also know the Korean space community has worked very closely with NASA. Any plan to unite or integrate, Sentinel-4 GEMS and Tempo data and create, hemispherical or even global products?
I think I should pass this question to Professor Jun Kim. He knows better than me, but as far as I know, there is a CEOS community. It's CEOS community, and they have regular meetings to generate consistent satellite data between GEMS, Tempo, and Sentinel-4, from generating the same type of file structure and everything. So in this meeting, I believe there should be some discussions about the kind of collaboration that you mentioned, and yeah, I think I can answer this question after discussing with Professor Jun Kim. Yeah.
Mm-hmm. Yeah, I think that'll benefit the air quality and health community tremendously, given the the issue of long-range transport and intercontinental pollution migration. Now we have a question for Sally, and this the question is, can you say a little bit more about your points on the inequalities on cloudy versus clear sky days? Are there increased exposure inequalities during cloudy days that the satellite cannot capture?
Well, I think that our results are limited to New York City and Newark. I'll caveat it by saying that, but we don't, we can't see in our work below on days that have that are very cloudy, where there's low observational coverage. We don't see those. We can't incorporate them into our work. We do find, though, that the surface concentrations are higher on average in New York City and Newark on those days. And because we find really strong correlations between the inequalities and the overall pollution level, that would suggest we're missing a piece of information there.
Mhm. All right. Okay. A couple other questions. One is it's more of a general question towards all three speakers. What is the biggest hurdle in your particular field of study? I know it's a broad question. Who likes to start?
Guess I can go. I would just say the vast amount of data that satellite data provides, I think, is intimidating to many people. And also the units can be intimidating to many people. So I think there's this logistical problem that many people are interested in using satellite data based on conversations that I've been having. But there's this computational pain point and also file format pain points where people are interested in using it, but then don't have the space. Often, I know with Tempo, we're going to need terabytes and terabytes of data storage to sometimes process the data. So this can be an issue. But I know that there's resources that NASA is trying to build out, and some of them are really excellent. And I think getting those publicized, NASA HACAS has a list of tools that are used publicly. Check out the website again, hacas.org. But yeah, I think that's one major logistical issue. I think there's other things as well. I think the surface people are concerned about using column contents to estimate surface concentrations. I think that's particularly relevant with AOD to PM2.5 surface conversion, but also NO to a column to surface conversion. So I don't know. Those are two kind of broad answers, but I'll let others comment on this.
Sally, you want to go next?
Sure. Yeah, I would echo those ideas. I think also, just in our own work, not just in terms of the satellite, but in terms of the whole observations, the whole sort of suite of observations that we use, is we're often using them to do something that they weren't designed for. So I think that presents a unique set of challenges. I think we understand satellite observations better when we, sort of try to use them in sort of new ways. And, there's a feedback, sort of learn more about the uncertainties associated with, for example, understanding NO2 inequalities, and learn things more broadly about the satellite data as well.
Yisong?
Yeah, in my specific field, I work mostly on producing satellite data. So once we produce the satellite retrievals, we need to assess them and improve them, mostly through validating with other observations. And it's relatively hard for some species to obtain reference observations to use for evaluating the GEMS and other satellite observations. For example, we have relatively many samples of ground measurement for NO2 and SO2, but at least over Asia, there are less data for organic compounds such as glyoxal. And so to assess the accuracy of the GEMS data products and to improve them, we need to collaborate with many scientists and integrate different types of measurements, including ground, airborne, and spaceborne. So in that way, we will be able to produce more accurate satellite data. Yeah.
Thanks. And a related question to that is, given the advantage of satellite data, which comprehensive spatial coverage, people tend to kind of view them as sort of universally accurate or universally inaccurate. The reality is the quality of the satellite data products may probably will vary in different geographic regions. Are you aware of any kind of systematic assessment or reports on the variability of data quality, especially related to NO2?
Yeah,
Anyone? Oh, okay.
I believe there have been some field campaigns to evaluate satellite data products all over the world. So for example, for TruPoMi, there have been some reports on their websites about the validation results of TruPoMi, NO2, and other species products. And recently, there have been a GMAP campaign in South Korea to evaluate the GEMS observations. So if the results are settled down and there could be some reports to interpret the GEMS data better, I think, yeah.
I see. And same question to Dan and Sally. When you conduct, national scale studies, how do you treat that, uncertainty in the product?
Yes, I can go next. Well, I do want to give a big kudos to the KNMI team who's released a new algorithm in the last couple of months that is an improvement. And so I think one important thing is to make sure you're using the latest version of the algorithm. Just go to the TruPoMi NO2 website and it'll be there. So I really want to, it's a very large effort that they have done. And yes, again, it's very important for the community to have a lesser bias. There previously had been a slight low bias in the algorithm in urban areas, and there's still maybe a small low bias that's not as large. Regarding uncertainty, yeah, I think averaging over longer timeframes is gonna get at that question. Day-to-day variability is, sometimes it can be trusted, sometimes it cannot be. Yeah, taking longer timeframes is helpful. And then I guess I'll emphasize that the field campaigns at NASA and other agencies that take on are really critical to do this, so to evaluate the product and really getting a very good understanding of the uncertainties. And I think it varies from location to location. I think that I think there is probably less uncertainties in the United States and in Europe because we do have these field campaigns, and it might be more uncertainty in Africa, even though it's the same algorithm, because there aren't the same field campaigns.
I would just add, we had done our daily inequality analysis in New York City. We had started that last year, so we had used the currently existing version of the satellite data. We recently updated it. I will say that a lot of it dramatically improved the uncertainties in our data, the noise in our data. You could really see quite an improvement there. Yeah, I mean, I think that for us, it's just a matter of identifying what we're trying, sort of identify exactly what we're trying to say, what we want to show, and then being really careful in our analysis around those points. And that's really how we've approached it. We've done a lot of work that's really always been oriented around, like, are we underestimating or overestimating differences between neighborhoods? And are our inequality estimates biased high or are they biased low? And in general, what we've found time and time again is they're biased low all the time. From a policy perspective, I think that there's, it's important to know that, but also perhaps there's some that's somewhat advantageous because we can say, we know it's at least this much. We're not overestimating it. We're underestimating it. perhaps it gets, it gets received differently if it's an overestimation. But I mean, we've seen in our own work, that there's, what we saw in many other cities was perhaps not, we couldn't do exactly the same things that we could do in San Francisco and Oakland because of the unique geographies of those places. So I think just, keeping track of what we're trying to show and being really clear about, how we're sort of orienting our uncertainty analysis around that.
Thanks.
I think there's a lot to learn there too, though, right? There's a lot to learn from those differences. So it's also an asset in some respects.
Yeah. Now Heather has a few more questions.
Yeah. So Dan, these questions came in during your presentation, but I think both Hisong and Sally could speak to these as well. So I'll ask them in a general context. The first one is, so one, when you're looking at like using satellites to get information about emissions, how does like cloud cover or different canopy covers impact the ability of the satellite to get those emissions? And then also on the same token, for both ambient and emissions, are there cloud screening algorithms and things like that in the satellite products that account for clouds?
Yeah, I guess I'll go at this question first. Yeah, so when I'm filtering the Tropomi data, I'm using a QA flag, which is it counts for areas of high clouds. And so that's why some of the images I showed and Hisong showed there's missing data. What's going on underneath those clouds is a tougher story. It's tougher question to answer, and that's because there's no information. So we really need to rely on any type of surface measurements we have during those timeframes. As Sally alluded to, typically NO2 will be larger in the presence of clouds than in the presence of clear skies due to NO2 being photolized during strong amounts of solar radiation. With that said, there are some procedures that can be done to try and estimate what's going on with the clouds. I know that NOAA does this a little bit for PM 2.5, and trying to understand using some type of estimation between the ground monitors to get at what's going on going on underneath the clouds. So there's ways around it, but it really is relying on the ground measurements.
Hisong, do you want to speak to the cloud impacts from the standpoint of GEMS?
Yeah, so basically how to treat the cloudy pixels at the moment for GEMS is simply discarding those pixels because they have a larger uncertainty compared to clear pixels. We lose some data over cloudy pixels. So if we want to generate some continuous maps of air pollutants, then at the moment we average the data for a given period of time to fill the gaps. So as described earlier, we need to rely on surface measurements at the moment, and there are some other methods like kriging or using chemical transport models combined with satellite data, but it's harder to fill the gap in cloudy pixels only using the satellite data sets. Yeah.
I might just add, in for example, in our own work, where we see the work that we're doing as being really useful to inform decision-making around environmental injustice, to design policies, to implement them, to evaluate them. The sort of exact differences on clear and cloudy days, that's important, but you can still do those other things even in spite of that uncertainty. So things like, where is NO2 highest within a city? Where should regulations target emission controls? Which communities are most burdened by combustion sources? Where is there no ground-based monitoring, and where should there be ground-based monitoring? I think that these are really, really important questions that can be answered still, in light of this uncertainty and others.
Yeah, that all makes sense. So along the same lines with ground-based monitors, here's a question related to using the satellite information, which sees the entire column, versus what the surface concentrations actually are. And so this question is related to whether or not there's differences regionally. So for example, LA versus New York City, in that surface and column relationship for NO2 that impacts the relative ground level NO2 concentrations between cities and regions, making it hard to compare with the satellites. So I don't know, Dan, this came up while you were speaking. So I don't know if you want to take a first shot at this, and then Sally and Hee-sung also can chime in.
Yeah, I'll take a first shot. I think it depends on your application in general. I think there are certain applications where just like a rough spatial estimate of pollution is needed by an air quality manager, for example. And in those cases, I mean, you can just apply some type of very rough correction to get from column to surface concentrations. With that said, I don't, that probably wouldn't stand up in it definitely would not stand up in a scientific publication. So, and there's other ways to do that. So if you want a relatively robust estimate, I would recommend doing it by region, trying to do this column to surface conversion by region, and even like California has many different microclimates, so you might get different variation at this column to surface variation even within the state of California. So I think it depends on your application. If you're just say interested in Los Angeles, then you would want a Los Angeles surface to column estimate, and there's various ways that you could get a very detailed way of accounting for that. And so yeah, it depends on what your application is and how much effort you want to put into it. But I think there's easy ways, and then there's much more difficult ways, and both can be relevant depending on your application.
I might just add to that, and we're really limited in what I can say here in terms of the United States, but we looked at the column to surface relationships, and when we looked at the 52 cities across the United States to look at the role of diesel trucking in inequality, and there are just 20 cities that have at least four monitors. So, and there are many cities that have no monitors. So it's this isn't a case of NO2. There's, sort of ozone observations are more, there are more ozone observations, for example, but it's a tough question to answer too, I think, from some of the limitations of the observations. Last time I checked, there were about 400 NO2 monitors across the United States. And they don't exist everywhere. So it's a tough question, I think, but an interesting one for sure. Maybe places, things like coastal location, or, you could think of a number of factors that could come into play.
And Hee-sung, do you have anything you want to add to that?
I just agree with Dan and Sally. I've seen various methodologies to estimate surface concentration from columns. For example, as a simple method, some studies use PBL height to convert molecules per square centimeter to ppm or ppb. And there are some other methods using machine learning and other more complicated methods. So there are various choices to do this, and yeah, it's I think it's a complicated work to do. Yeah.
Yes, thank you. I agree. It's very complicated. So we're out of time now. I just really want to thank all three of you for giving talks today. Each of you highlighted the cutting edge research you're doing and how you're integrating these satellite products into your air quality studies. Dr. Goldberg gave us a great overview that highlighted uncertainties and limitations of satellite remote sensing, but also really illustrated where satellites can provide information that we can't get from other sources, both from an emissions standpoint and from the ambient air pollution concentrations. Also, the advancements in remote sensing capabilities on geostationary satellites are really exciting to see. And Dr. Chung showed us interesting results from the recently launched GEMS instrument that really just nicely demonstrates the advancements that those remote sensing products for multiple pollutants that will be available from GEMS and the other upcoming geostationary satellite missions. And then we move from that into this very local scale where Dr. Passetti showed examples of using satellite products to estimate spatial gradients of air pollution concentrations and then relate that information to socio-demographic factors. And that's really critical because air quality monitors alone can't capture those spatial differences that we have in air pollution concentrations. And it doesn't give us enough information about what every community is experiencing. So integrating the spatial information from satellites is important to quantify the inequalities that have resulted from environmental racism. I also want to thank all of the attendees for coming today and asking great questions. Your input is really valued and it helps us achieve the goals of this workshop, which is to get questions and comments that provide inputs across many disciplines. All of these disciplines are necessary to explore where we can use these satellite products in health applications. And again, all of the speakers today touched on the importance of integrating different types of data into frameworks that help us understand the spatial and temporal air pollution distributions. And our discussions today will help us kick off our next webinar, which is roundtable discussions. And I'm really looking forward to seeing how we have discussions about integrating satellites and observations, including those from low-cost sensor networks, and brainstorming future directions our community can go to leverage these satellite products, especially in regions that do not have air quality monitors. And so with that, I thank you again, and I'm going to turn it over to Allison to close out the session.
Thank you, Heather, for those closing remarks. You thanked everyone as well as I could. So thank you all for coming and contributing. We still would like to hear from anyone we haven't heard from before. You can do that by filling out the pre-workshop survey where you can tell us about the work you're doing or what you want to learn about satellites and remote sensing. We'll be using those surveys to prepare some questions to discuss at the roundtable discussion, which is the final session of this workshop and will be held on Wednesday, May 18th. If you haven't already registered, you can find the link to do so in the chat. We also want to invite you to the HEI annual conference. This year, it will be at the end of June in Washington, DC in person. There will also be a virtual opportunity where you can register and view some of the sessions online. The topics will include population health, environmental justice, air pollution, climate change, and many cutting-edge research methodologies. So thank you for joining us today, and I hope we'll continue to discuss these issues of satellite-derived air quality and how those data can be used for health going forward. Thank you all again.